In the previous video, we learned about the Jarvis March algorithm, an algorithm to find the convex hull of a set of points. But the downside of it was its time complexity of n times h, where n is the total number of points and h the number of points on the hull, because n times h is close to n squared when h is close to n, which is quite slow. Today, we will see another algorithm that solves the same problem but more efficiently, the Graham-Scan algorithm. Quick reminder, the convex hull of a set of points is the smallest convex polygon that contains all the points inside it. Convex polygon means that all interior angles are less than or equal to 180 degrees. Okay, imagine that we have this set of points. We start by finding the bottommost point, the one with the smallest y-coordinate. Let's name it P0. Now, we have a polar angle between P0 and each other point. What we do is that we sort them according to the polar angle. Here is the first one, then the second one, then the third one, and so on. Basically, we sort points according to their polar angle with the bottommost point. From here, we can start working. We will traverse the sorted points. We start by putting the first 2 points on the hull, and from here, for each remaining point, we check the orientation of the before last point on the hull, the last point on the hull, and the actual point. For example, with this one, the orientation is counterclockwise. We can directly put it on the hull. It becomes the new last point. Next point, here the orientation is not counterclockwise. It means that the last point shouldn't be on the hull. We remove it. Now the orientation is counterclockwise, we can insert the actual point. Next point, counterclockwise, we directly insert. Next point, counterclockwise, we directly insert. Next point, the orientation is clockwise, we pop the last point. The orientation is still clockwise, we pop the last point. And here the orientation became counterclockwise, we can insert the actual point. Basically, we keep popping until the orientation of before last, last, and point becomes counterclockwise. In other words, we remove all the points we inserted before that don't need to be on the hull. Let's continue. Next point. The orientation is clockwise, we pop. The orientation is now counterclockwise, we can insert. Next point, counterclockwise, we insert. Next point, counterclockwise, we insert. Next point, counterclockwise, we insert. Next point, clockwise, we pop. Clockwise, we pop. Still clockwise, we pop. And now counterclockwise, we insert. And the process continues like that until we finish traversing points. We finished traversing the points, we got the convex hull. What we did here is that we used the stack to store the points that are actually on the hull, then for each new point, we keep popping until we have a counterclockwise rotation between the before last point, the point on top of the stack, and the actual point. By doing so, we have counterclockwise rotations only, which produces the convex hull of the set of points. Before being able to implement this solution, we must know two things: how to calculate the polar angle and how to find the rotation of 3 points. For the polar angle, we use arctangent, a trigonometric function. And for the orientation, we talked about it in the previous video, that you should watch by the way, because we also used it in the Jarvis March algorithm. Basically, we just calculate the slope of the line that passes from P1 and P2, the slope of the line that passes from P2 and P3, and we compare. Now we can start writing our solution. We start by finding P0, the bottommost leftmost point. We write min points, where the comparison key is the y-coordinate, then the x-coordinate. After it, we sort the points, where for point P, the key is the polar angle between P0 and P, then the distance between P0 and P, to say that if 2 points have the same polar angle, the one that is closer to P0 comes before the other one. Now we can start working. We first create hull, which is the stack that will contain points on the hull, then we traverse points. Remember that for each point, we keep popping while a certain condition is still true. That condition is not having a counterclockwise orientation between the before last point, the last point, and the actual point. In code, the before last point is hull of -2, the before last element, the last point is hull of -1, the last element, the one on top of the stack, and the actual point is points of I. We also need to make sure that there are at least 2 elements in the stack, otherwise we don't have a before last element. In code, we write while length of hull is greater than or equal to 2, and the orientation of hull of -2, hull of -1, and points of I is not 1. 1 means counterclockwise. We pop. After we finish popping, we just push the actual point on the stack and we continue, as we were doing in the example. After traversing all the points, we just return the hull. And that's how the Graham-Scan algorithm works. For the time complexity, finding P0 costs O of n because we just traverse points. Sorting the points costs O of n log n because calculating the polar angle is an O of 1. Then we have a loop that is traversing the endpoints. Here, even if we have an inner loop, but the total number of iterations done by the while loop is n, because every point is pushed and popped only once, and we have n points. So in total, this loop costs 2n. We get T of n is equal to O of n plus O of n log n plus 2n, which gives an O of n log n time complexity. And for the space complexity, we got O of n because of the hull. Okay, now we've seen 2 convex hulls algorithms, but it would be good to see an application of convex hulls. This is why in the next video, we will see how can a robot find the shortest path to go between 2 points by avoiding a polygon obstacle. See you in the next video.